So tonight's speaker is Colin Murphy. Colin is a chartered engineer with Engineers Ireland and is also the engineering manager for the Thames Tideway project on the west section. And he's here tonight to give us an update on the project progress to date. There will be some time for Q&A at the end. And for those viewing online, could you please use the Q&A function rather than the chat function on Zoom to raise your questions, and I will ask them to Colin at the end. So I'm now going to hand you over to Colin. Thank you very much.
Well, thank you very much for the invite to speak to Engineers Ireland tonight. Much appreciated. I'm going to talk to you tonight for about 45 minutes, if not 50 minutes. And as Philip said, there'll be some time for questions and answers after that. So thank you. My name is Colin Murphy. I'm engineering manager on Tideway, on the west section of Tideway. I'm going to talk you through the following elements of the project. So I think before we can talk about project progress, I really do need to bring you up to speed on what the project is all about. So I'll do a little bit of a recap on project need, project scope, what it's all about, the solution development, how we got to where we are today and why we're doing it, some of the design challenges we've had to meet on the job and how we've implemented solutions to that, and then I'll bring you into some focus on some of the things we've been doing and some specific interesting bits of the job, and then a little bit of a look ahead on where we are now today and where we're going for the next couple of years. So let's get into it. So what is Tideway? Well, it's the biggest infrastructure project ever undertaken by the UK water industry. It's approximately 25 kilometres of sewage interception, storage and transfer tunnels. She ranges in the depth from 35 metres to 65 metres beneath London and the River Thames. And it's made up of 3 tunnels. So we've got one main tunnel, which ranges in diameter from 6.5 metres to 7.2. And then we've got 2 offshoot connection tunnels, which range in diameter from 2.6 to 3.2 metres in diameter. The project is made up of 24 construction sites, 11 of which are riverside. So that's beside the river or actually within the river in New Foreshore, which we've constructed. And Tideway, along with our sister project Lee Tunnel, which we connect into at Abbey Mills, between them they provide 1.6 million cubic meters of storage capacity for raw sewage in London, which in typical civil engineer hydraulics parlance is the 600 Olympic swimming pool equivalent, which is the standard that we go for. So where are we? What's the route? So we run from west to east. So we're running from number 1 up there on the Ealing border. So we run from Acton down just south of Hammersmith Bridge. Then we follow the river down through Barnelms into Wandsworth, where we hook up with the Frogmore Connection Tunnel, which is a 2.6 metre diameter coming in from south Wandsworth. We carry on then into central London to Battersea, the Battersea region up past the Tower of London, under Tower Bridge, and then we hook in one of our main drive sites at Chambers Wharf, which is number 17 on this plan. That's where we made the Greenwich Connection Tunnel, which comes in from southeast London, Lewisham direction, the Greenwich pumping station site. And the main tunnel then continues on up through 21 and 22, coming landside and following the alignment of the Limehouse Cut to meet the existing Lee Tunnel, which was built in the early 2000s between Abbey Mills and Beckton Sewage Treatment Works. So in terms of flow conveyance, what can we handle? So we're designed to carry 140 cubic meters per second. So just to give you a sort of a comparison of where that sits in terms of flow, the average median flow in the Thames on a sort of a normal summer's day is about 66 cubic meters per second. So we could handle a fair chunk of the Thames if we needed to. Obviously, that's not the intent of the Thames. It's just to give you a visual feel for what we're trying to do here. So when we talk about flow, we talk about design ranges, and what we're trying to take, we take sewage up to the 1 in 15 year probability storm event. And the thing with Tideway, and it will become clear in a second, is that you can design a tunnel as large as you need it to be. In our case, we designed the tunnel for what we're physically able to take from the system. So the Thames Water Network can only physically deliver a certain amount before the Thames network itself would experience flooding. So that for us is the 1 in 15 year probability storm, and I'll go into it a little bit more in detail in a second. So I've mentioned the 140 QMEX, running full bore. So when the tunnel is fully operational in an extreme weather event, if we were hypothetically connected to the Millennium Dome, we could fill the Millennium Dome in about 4 hours with raw sewage. Our site design flows, which we capture at a number of CSOs, range in size from 1 cubic up to 55 cubics. And a cubic, so that's the cubic meter per second, just to give you an idea what that looks like in sewage coming at you. We talk about the 4 cubic yard mini skip, you know, sort of domestic builder skip is about 3 cubic meters. And at one of my sites, Hammersmith, we deal with 43 cubic meters a second of sewage. So that's about 14 mini skips of sewage a second that we're trying to turn in a typical storm event. So to understand the route, you kind of need to understand a brief history of London sewage. I'll make this brief, but in a nutshell, late 1800s, early 1900s, Bazalgette, famous civil engineer here in the UK, constructed the modern sewage system in London. And that was comprised of about 1,100 miles of street sewers, which connected into about 82 miles of strategic main, which run from west to east in London. And those mains are arranged in high level, middle level, and low level sewers, ultimately aiming to convey sewage, raw sewage, to East London, to the treatment works in Beckton and Crossness. And when Bazalgette designed this system, he designed in a series of overflows. So he knew that at some point in time, because the system captures both rainfall and sewage, with certain rainfall events and increasing in population, the system would become inundated. So he built in a series of combined sewer overflows along the river. And this is what it effectively looks like today. You know, this picture on the top left is probably about 6 years ago, but that's a Thames Water operative in the low level line on embankment. So those of you familiar with the embankment in London will recognize the cross section at the bottom of this plan here. So you've got what we call today the district line, and just to the west of that, or sorry, to the south of it, the left in this picture, you've got the low level sewer, and then you've got a subway containing strategic utilities through the embankment there. And what we're effectively dealing with is the CSO, which comes off that low level sewer. So when that low level sewer is inundated and full, that will overflow. So Bazalgette designed the system. He designed his sewage system, and he designed the overflow system to cater for 4 million people. 4 million people in London was surpassed in 1920. In 2019, we hit 8.8 million, and 2160 is projected to hit 16 million. As a result of a massive increase in population, way beyond what Joseph Bazalgette would have expected, coupled with rainfall intensity increase, what we've seen through the years is a massive increase in the amount of discharge into the river. So in 2014, we had a bad year in terms of raw sewage being discharged into the Thames. There was approximately 62 million cubic meters of sewage discharge into the tidal Thames through London. And that equates to about 50 discharges on a typical year. So that's raw sewage in a rain event discharging straight into the river. And in order to trigger these overflows, you need about 4 millimeters of rainfall to occur in London. So the system is running at about 60% full on a typical dry day in the middle of the summer. And this is what a CSO looks like. So this picture here is taken of a CSO just underneath Vauxhall Bridge. The flow discharging here is approximately 6 to 10 cubic meters. You know, I mentioned earlier some of our sites are 4 times what you're seeing in that picture there. So fairly substantial flows and big discharges. So on an average year, what we're seeing is 39 million cubic meters of sewage discharged into the river. 50 to 60 CSO discharges in a typical year. Obviously, that's got an environmental impact because the river is tidal. That means that the sewage pollution and the effects remain in the river for weeks, affecting the dissolved oxygen content and ecological health and habitat in the river. There's a human impact in terms of the frequency of discharges. It's a threat to river users who recreate on the river and walk along the foreshore. And finally, there's a legal angle to this. Ultimately, the UK fails to comply or did fail to comply with the EU Urban Wastewater Treatment Directive. So the tidal Thames wasn't achieving good status. So Tideway was developed, and I think it really began its fruition back in 2001 with the strategic study. Went through a whole series of iterations and optioneering, but ultimately it boiled down to these 4 options. So one was to try to see, could you control the rainfall high in the system? So at source SUDS. Could you control and store within the system, online in the system? Could you deal with it at the CSOs, so actually capture it at the point of discharge into the river? Or could you do something within the river to improve the oxygen content within the river? And really with the volume and scale of what we're talking about in terms of discharge, number 3 there at the CSOs is really the only solution you can have for a problem of this scale in terms of the impact to London. But the quantity of land that you'd need for the likes of SUDs or online storage just wasn't tenable. So in terms of capturing sewage at the riverside, you then need to understand what you're going to do with it when you get it there. And that had 2 problems associated with it. So one, you had an overloaded sewage treatment works system in London, and you had an overloaded sewer network. So there was 3 solutions came up to deal with those 2 problems. So one was the sewage works upgrades, which were taking place in the early 2000s. Lee Tunnel, that came on in sort of 2010 onwards, from Abbey Mills to Beckton, and then Thames Tunnel, which picks up the bulk of the sewage which runs through the extended area of London. And that's broadly what those 3 solutions look like. So Lee Tunnel from Abbey Mills to Beckton, and then Tideway off to the left there coming in from Acton. So in terms of developing the scheme, we had a couple of key fundamentals we needed to adhere to. So we wanted to maximize the use of the sewer system, so maximize the discharge from the sewer, take everything that the sewer could deliver to us. Maximize the use of the capacities at the treatment works, so deliver everything that we were receiving straight to the treatment works as much as we could. We wanted to control the CSO discharge frequency, so control it from today's 50 or 60 down to Bazalgette's original design standard of 4 discharges per year. We wanted to do all that without increasing flooding risk. We didn't want to have extensive above ground structures where we might need to control water levels. And we were very conscious that we'd need to reduce the risks associated with adverse pneumatic and transient conditions. That's something I'll get into a little bit later. That is a fundamental issue with a project like this. And we wanted simple operating rules. We didn't want to rely on meteorological forecasting and computer modeling to operate this thing. We wanted a fairly straightforward, dumb system that would take sewage as and when it needed to. And this is effectively what it looks like in schematic. So on every CSO, which is the red pipe you can see in the center, we have an interception chamber, which is effectively a box, concrete box. Those boxes range in size from anywhere from 6 meters squared right out to 10, 15 meters squared. They go down to approximately 15 to 20 meters in some of our sites. Some of them are cathedral-esque in size. We capture the CSO flow, we capture the sewage, take it through a connection culvert into a drop shaft and drop it anywhere from 25 meters to 65 meters down to a connection tunnel where we take it into the main tunnel. So in order to develop the scheme, we went through 6 years of planning. I was involved in the project at that stage. We took a long list of 370 odd sites down to today's 24, and we took it through DCO, ultimately concluding in a DCO acceptance in 2016. And at that point in time, it was quite interesting. As a project team, we had 2 problems. One was, we obviously needed to procure and tender contractors to build this project. At that stage, we knew it was going to be a £4.2 billion scheme. But we also were looking for a client, so that the project was of a scale that it couldn't sit on Thames Water's books effectively. It was just too large a project for Thames Water to handle as an entity. So whilst we were tendering for contractors and procuring contractors, we were also tendering for a client. We were tendering for someone to be in charge of us effectively and run the project in the future. So that ultimately that became Bazalgette Tunnel Limited, which is a private entity, private finance, made up of a series of pension firms. And I think approximately at the moment about 1.7 million UK pensioners will have some sort of indirect investment in Tideway via their pension provider. So that's the route. That's what I showed you earlier. In terms of delivery, this is how we're delivering it, and I've been doing so for the last 8 years. So in terms of the central section, that's been delivered by a JV of Ferrovia Langer Work, and their main task is to tunnel concurrently in 2 directions from a drive site located at just beside Battersea Power Station and Kirtling Street. So they drive west to pick up with the west contractor, which is Morgan Sindall, Balfour Beatty, Bam Nuttall. And they also drive east to pick up with the eastern contractor, which is a JV of Costain, Vanchy and Bashi Solantash. That's the drive strategy in east. So we drive north from Greenwich Pumping Station to connect in at Chambers Wharf. And we drive east from Chambers Wharf to Abbey Mills. And then in west, similarly, we drive west up to Acton and northwards from King George's Park into our main drive side of Carmouth Road. We also have a system integrator, Amy, so their job is basically to tie it up all at the end, bring all the telemetry on stream and make the SCADA systems work so that it can be controlled from Reading ultimately in the future. And then Jacobs are the project-wide program manager and project manager, and that's who I work for. So how it looks like, so you'll recognize this cross section here on the right hand side, that section through the district line. Then you've got that's the low level CSO line. We take an overflow from these CSOs, we drop it into a connection culvert, take it into the shaft, and as I said earlier, we take it down what we call a vortex drop tube within the shaft, and then away to the tunnel. And I'll get into more details in a second about that. So in terms of developing the scheme, the challenges for us were many. So land and spatial. So the CSO interception sites needed to be immediately adjacent to outfalls or the CSO alignment. And that meant that our 24 sites, our 24 CSOs, we needed 24 sites in central London, close to or at the river. We needed 3 main drive sites. A drive site is typically about the size of 2 football pitches. And at our CSO only sites, so those sites where we're not driving a tunnel from, we're just picking up flows, they're equivalent to about 1 to 2 tennis courts in size. And of course, on each of these sites, we need a shaft, which is anywhere from 6 meters to 25 meters in diameter. And we're trying to do this in a congested urban environment, so quite challenging to find those sites originally. Ultimately, we aim to use brownfield land. We aim to use Thames Water sites where we could, but in the main, where we couldn't utilize existing land, we aimed to provide new land within the river in new foreshore sites. And we've got some examples of that, such as Blackfriars and Putney, where we're building new public amenity out into the river. And we were keen to take an opportunity for environmental mitigation and betterment right throughout the scheme with a sort of a legacy mindset. This job isn't just about picking up sewage, it's sort of about reconnecting London with the River Thames and reintroducing the river to people who might have turned their back on it over the years, rather than have it as a main sewer. Let's get people using it and recreating it again. Just for those of you unaware, a typical foreshore site looks like that at the top left. So that's a sheet pile cofferdam. A picture of a typical small shaft on the bottom. That's a segmental shaft. I think it's a Jackson segmental shaft. And then a drive site here, top left. Pretty large enterprise. And that's a picture of the TBM for the Lee Tunnel just before she went down into the drive shaft. And I just put this picture in here to give you an impression of what a big TBM like that looks like in a large shaft. So that's a 20-meter internal diameter shaft, 74 meters deep, with nearly a 9-meter diameter TBM inside it. And you can see that it fits in quite snug. So these shafts need to be big for a reason. We fill them up quite quick. So in 2016, I think this is more or less what we were at. Chambers Wharf was setting up the marine logistics and cofferdams were being constructed right throughout London. We were just about to sink shafts or just about to set up sites back in 2016. And thinking about setting up sites, construction logistics, many of you will be acutely aware of the sort of congested urban environment we operate here in London. Road safety concerns is a huge issue. And we took a very firm rule really for our contractors that we needed to move more by river, use the river as much as physically possible, and where you can't use the river, that needs to be heavily justified. Air noise quality management, huge issue for us. Understanding the quantities, volume, and construction duration. So 24 sites needing concrete, needing materials. We all can't feed them all simultaneously, so the construction program needs to be fairly tight in terms of understanding what the industry can actually deliver to Tideway in order to build Tideway. Personnel challenges. We knew that Crossrail was on the go at just prior to the start of Tideway. We knew we needed to slip in just after Crossrail and sometime before high speed too, because at the peak of Tideway about 2 years ago, we had about 3,500 people on the project. So that sucks up quite a large amount of the industry in the UK and Europe. When we talk about environmental mitigation, we talk about things like acoustic sheds over shafts, and just to give you an idea what an acoustic shed looks like on one of our sites, that is an 80-meter long, 26-meter wide, 21-meter high building over a 25-meter diameter shaft, within which we're tunneling from, and that building itself is sitting on about 160 odd piles. So these enterprises are fairly heavy civil engineering projects in themselves, to enable yourself to actually begin what you wanted to do in the first place. Interfaces with existing infrastructure is a huge project in itself. For some on Tideway, you can see the numbers there for yourselves. We interface with about 20 kilometers of river walls, 75 odd bridges and 1,300 buildings, not to mention 24 listed buildings and 45 odd tunnels. And of course, challenges of tunneling through London. This point here is really what drove how our contracts were split between West, Central and East. So our West contract is predominantly driven through clay. Our Central contract is predominantly in sands and gravels in the Thames sands. And then we get out into East, which is chalk. So what that means for us is that we're using more or less, with the exception of rock, we're using more or less every form of TBM and tunnel driving technique you have out there. We've got earth pressure balance, EPB, TBMs, slurry shield, TBMs, open face, pipe jacking, you name it, we're probably doing it on Tideway. Also lends itself to multiple shaft construction techniques, secant piling, sheet piling, SCL, spread concrete, segmental shafts, and diaphragm walls. The specific engineering challenges for us on the job in terms of design and what we're trying to do, we need to achieve a 120-year design life in a sewage environment. We really need to understand and manage and dissipate energy and minimize air entrainment through the use of the vortex drop tube. So air in a tunnel such as this is a big deal. It's something to pay attention to. We need to understand how to deal with that. Provide mechanical ventilation and air treatment to keep the tunnel environment fresh and reduce the risk of odorous air release from the shafts. And we needed to intercept sewage whilst keeping the sewage network alive. That old cliche of open heart surgery. Well, you've got the patient still alive. We more or less have to do here in terms of the Thames network. And then we need to operate and maintain it and provide the land to do so for 120 years. In terms of hydraulics, I've mentioned the flows. In order to understand those flows, we undertook catchment modeling. We understood pneumatics and transients. I'll explain that in a second, and undertook a lot of CFD modeling. And then we undertook a couple of years worth of physical modeling in the UK and the US to validate our designs and validate the modeling that had been done over the number of years. Now, I've mentioned pneumatics and transients. Surges and transients were a problem that we need to be really aware of. And for those of you who've ever really designed rising mains or pressurized mains, you'll be familiar with the term backhammer, where if we've got a pressurized pipe, there's energy that you put into that pipe. And when the flow gets to the end of the pipe, that energy needs to go somewhere. Now, in our case, we put a lot of energy down into that tunnel. All that energy heads to Abbey Mills. And when it gets to that end shaft in Abbey Mills, that energy comes right back at us, right up through the system. So what you start to see in terms of a hydraulic grade line as you look in section across the tunnel is that your hydraulic grade line starts to bounce, you start to get a wave motion in the tunnel. And that means that your shafts, as they're filling, your shafts in terms of air pressure start to operate like a piston. You start to get a piston effect, but a piston effect to the tune of about 10 meters per second of drop. So quite substantial, really fast, high flow changes. And they can lead to damage. We know from previous projects in the United States that they got that wrong and didn't quite pay enough attention to this issue. And you've seen damage on shaft lids and access covers being blown off. So that was a big deal for us to get right. We needed to be aware of large storm events. You could have heavy rain in West London, you could have no rain in East London, and the system needed to manage that. And then we needed to model and understand how we're going to take air in and out of the tunnel. I won't get into this, I'll move on. So what this all looks like in terms of engineering and how we actually do it. So this is one of my sites at Dormay Street in West London. So you can see on this is all built now. This is in the ground, currently being landscaped. What you can see on the left there is the interception chamber. We drop flows about 6 meters, turn them through into a connection culvert, and then into a valve chamber. So in every one of our sites, we've got a valve chamber. We've got a penstock gate, which is anywhere from 2 to 3 meters square. That allows us to control flow into the tunnel. The flow proceeds on through a flap valve that allows us to deny flow coming back from the tunnel. Flow goes through that flap valve into what we call a vortex generator, which you can just see at the top of the shafts here, just pointed out there, labeled there. So vortex generator and drop tube And what we do here is a bit, it's quite clever. It's a means of taking air out of large volumes of flow. So we want to avoid air bubbles in the tunnel. We take the flow, we squeeze it, so that generator gets narrower and narrower, so the culvert narrows. At the same time as it's narrowing, it's also dropping down a ramp. And we reach a throat, which restricts the flow, squeezes it, increases the velocity, and then we spit that flow against the inside of a tube. That tube is anywhere from 1 meter to 2.5 meters in diameter. We create a centrifugal force within the tube, so we push that flow to the outside of the tube. The air wants to come out. Basically, we create a vacuum core up through the middle of that vortex tube. Air comes out, air goes up, flow goes down. So that's good news, but now we've injected a hell of a lot of energy into that flow. So at the bottom where it drops out of the tube, we create a stilling basin. So in this example here, we've got baffle walls that are about 12 meters high to give us a stilling basin where we cam it all down, cam down that flow, and then it goes out through an egress and into the main tunnel and away. This is what CFD modeling of that setup looks like. This is a different site, but you can see just in the shaft there, you can see that twisting effect of the flow, the yellows and reds there. This is some modeling we've undertaken on air bubbles and where air bubbles get trapped within the tunnel. So we're aware that on some sites we would have had a bigger problem with air bubbles, and you might need to do additional baffling or additional restrictions down in the tunnel to try to capture that air and take it somewhere. This is an example at Hammersmith where we take it up through a vertical deaeration vent pipe, which is about sort of 30 meters long. And this is all backed up, as I said, by physical modeling just to evaluate and validate the scheme. And I don't know will these work, maybe they come across there, but you can just see the bottom right, there's some energy dissipation and deaeration at the shaft base. So that's showing all the bubbles being churned out and they're heading off the atmosphere up through the shaft. And you can just see that top one there. I don't know, will that work? It probably won't, so I'll move on. But you can see the twisting effect on the vortex tube on the right-hand side of the photograph up there. I won't show this video in case I blow up the webinar, so I'll carry on. But just what I wanted to give you was a feel for what that vortex generator looks like in real life. So I think this is August, I think this is about August 20. And this is us lifting in our vortex generator at Hammersmith. So it's an 1,100 ton crane. That was a big lift that day, and a really amazing day to see that being dropped into the shaft. I think there's about 1,000 tons of steel being lifted down ultimately into that shaft. This is a photograph taken from the shaft inverter of the pit bottom, looking back up the tube, just to give you a sense of scale. That tube is about 2 meters in diameter, roughly. So I've talked a bit about air. I've talked about probably a need to change air within the tunnel. So ultimately, what we have on the scheme is what we call the bookend approach to ventilation, which is we've got active and passive ventilation. So at either end of the tunnel and somewhere in the middle, we've got active systems, which are fans, which allow us to extract air out of the tunnel as the water level is rising. We can suck it out basically, and we can put air back into the tunnel as the water level is dropping. The passive sites are sites where we don't have fans, but we rely on the delta between atmospheric pressure and the pressure within the tunnel. So the air gets pushed out and the air gets pulled back in again as the water level drops. And what this looks like is that we effectively take air out at high level in the shafts through a series of ducts, and we take it through air treatment chambers, and we discharge them through ventilation columns. Now these pictures here show our scheme at Carmarth Road in Fulham. That's a 12-meter high ventilation column. But at the passive sites, those ventilation columns are circa 5 meters. And our architects have tried to work very hard to try to minimize the impact of a lot of these ventilation columns and try to feed off the legacy of other vent columns in London. That's an example that many of you will probably be well familiar with of a statue at Bank Station, and that is actually a vent. And we've tried to sort of mimic that idea of trying to hide it, but I think our architects decided actually they wanted to celebrate it, so it turned on its head. And we've got the design on the right hand side, which looks like this. This is one of our first ventilation columns. That's pure cast bronze from a specialist foundry in the Netherlands, and that was installed on one of my sites, King George's Park in Wandsworth in September 2021. That picture just in the background, or in the middle, sorry, you can see one of our kiosks behind the vent column, which has the green roof on top of it for environmental betterment. And air treatment, again, just another version of events with air being taken out the top of the shaft, taken through the air treatment chamber. And then in this particular example, the ventilation column is actually hidden within a kiosk building. MICA is a huge issue, mechanical, electrical, and instrumentation. That could be a couple of presentations on itself. I won't get into it in this talk because I'm conscious of time. But ultimately, we've a lot of equipment that we need to house on these sites, and very challenging spatial constraints on the site. So a lot of work has gone in to try to squeeze control equipment into kiosks and elsewhere. And this is one of our typical small sites. That's one of our sites at King George's Park. But this is just to give you an idea of the amount of access covers that we have on the job. You know, on our smaller sites, we've anywhere up to about 30 odd access covers. On our bigger sites, we might have up to 60. And that's all around differing access needs for differing maintenance events, whether you're getting into the sewers or you're getting into the shaft. They all have different requirements. Talked a little bit about environmental betterment. This is an example of a scheme we have at Dormey Street, which is an intertidal terrace, which is being completed as we speak. And this is one of our schemes at Barn Elms, which is quite an interesting scheme. Actually, it was quite a challenge here, because the idea was to try to blend the scheme into the background. So as you're on these playing fields in Barn Elms and you look down towards the site, you shouldn't actually be able to see it. But some of the interesting facts about this site here is that we've got a road to access the works down at the bottom of the site, which is about 1.1 kilometers. And effectively that's hard paved with recycled plastic. So it's a fully recycled plastic road. And the subbase was a recycled subbase. In fact, every element of that road is recycled in some format, which I'm quite proud of. Took a little bit to achieve that, but I think we've done a good job. This is a slightly older artist impression here, but the works are more or less complete. And for those of you who've been watching BBC archaeology, the Big Dig recently, you might have seen Barn Elms was on that. This is one of our archaeological sites where we found some interesting items. So just getting into it now, just taking you through some progress photographs from recent years. So just looking at tunneling, is a picture of a couple of different shafts here. So on the left-hand side, you've got a D-wall. There's a diaphragm wall shaft. The excavator being lowered down to continue the excavation in the pit bottom. We've got SCL sprayed concrete lining on the top right and bottom right as well. And then you can just see some, I think they're just getting ready to do some steel fixing on the pit bottom there. In that picture, these pictures here are probably about 2.5 years old, if not more. That's a shot from the bottom of Greenwich, looking up at that D-wall shaft. You can see the ventilation pipework coming down the side as temporary venting. A pretty epic shot, and you can just see that the lighting at the top is on the underside of the acoustic shed, which is similar to the one I showed you earlier at Carmouth Road. This is a layout of a typical marine logistics drive site. This is what we've got at Kirtling Street, or did have at the height of tunneling. So effectively on Tideway, we bring in all our segments by barge. Those segments come in to be stored on site in a kind of a just-in-time format, and the segments are taken down into that acoustic shed, down into the shaft, and then taken up by train up to the TBM and erected. Simultaneously, the muck is coming out the back of the TBM, and that comes back on conveyors, and then that's been taken out up for treatment. And you can see the sort of bentonite plant and settlement lagoons and that kit at the back of the site for dealing with muck and slurry treatment. But ultimately, we take muck away by barge to segments in, muck out, is what that layout is showing. And this photograph here is a slightly older photograph now, but that's just showing the construction of some of the marine jetties on the river to facilitate that. Here's a picture from last year. This is down east, Chambers Wharf, quite an epic picture in my mind. This is our TBM Selina being delivered to site on a 3,000-ton jack-up barge. And this is her being lifted into place onto the site at night. Fantastic picture there. Top right is a typical muck away operation on the job. We push our barges rather than pull them. That sounded like a pretty simple thing to think of doing, but that was a big change in the marine industry in London to push rather than pull. but that was done on efficiency and fuel and cost saving. On the bottom right, we've got segment delivery. Again, that's one of our tugs. That's a brand new tug that Tideway purchased for the job. That's called Felix. And Felix is an interesting tug because the cab can raise up and down to give the operator sufficient view of his barge. But when he gets under low bridges at high tide, he can scoot down to avoid a clash. Some more photographs there of segments arriving into Kirtling Street. I think that's in Central. Top right is some TBM parts being delivered to West a couple of years ago, and then that's some muck going past one of our main offices in London. I think overall the general conclusion here is at the moment we've achieved about 4 million tons of material that's been moved by river, which is 4 million tons which otherwise would have gone by road. I think by the time we're done we'll probably have hit the 5 million mark. So looking at a few photographs down below, so main tunnels, this is a TBM launch. So this is Selena, that's that TBM you just saw being delivered and lifted onto site. That's her down, just ready to begin her journey. This is a photograph from one of our west tunnels. This is main tunnel A in west. This is just showing us sort of a typical construction logistics crossing in the main tunnel there. I love this photograph. I think for anyone designing temporary works and thinking about the complexity of particularly tunneling jobs, this picture, there's a hell of a lot going on in this photograph here. This is at Carmouth Road, and what's happening here is that halfway up the shaft, I mentioned earlier that Frogmore Connection Tunnel comes in from Wandsworth and meets the main tunnel. It happens in this shaft. We've got a ballpark 3 meter diameter TBM halfway up the shaft, coming out onto a temporary works deck, which we've constructed 16 meters above the pit bottom. And on the bottom, you can see operatives and equipment which are feeding the main TBM, which is concurrently driving up to Acton. So concurrent activities here, one at height. And you know, that's a sort of a 750 ton TBM can that's ultimately sitting up there. So very substantial temporary works. That's that TBM post strip. So, you know, there would have been about 80 odd meters of equipment, you know, gantries and conveyors trailing behind that TBM at one point. But this is her. She's having her motor stripped out. I think she's had 6 careful owners before us, and now she's moved on elsewhere. These are some photographs of some breakthrough. That TBM I just described there, that was on that deck, is on the right-hand side. That's breakthrough at King George's Park. And on the right-hand side, that's main tunnel C at Central, one of our central TBMs breaking through. And where we are right now on the job today, we are predominantly finished tunneling. Most of the tunneling works is done except for east. So that TBM Selena, the photographs I showed earlier, she's the big TBM that's still going, but the remainder are all complete. So west tunneling is complete, central tunneling is complete. And now the big focus for most of us, including myself for the last year, has been secondary lining. The secondary lining of these tunnels is an extremely complex affair. We're trying to deliver concrete of sufficient consistency to be able to deliver, you know, pump it, get it up to the shutter, but maintain sort of quick cycle times, quick curing times, and being able to strike shutters as fast as we physically can to move on. All of our tunnels are primary and secondary lined. The primary lining is either a segmental lining or an SCL lining. And all our tunnels have approximately about 250 mil of secondary lining on the internals. In order to pour those secondary lining sections, we use an automatic shutter from Kern. In the case of my contract in West, is a typical shutter that they've developed for the job, which is an automatic shutter, automatic striking. This is that shutter undergone factory acceptance testing in Slovakia. Or Slovenia, sorry, I should say. And then that's her in position, doing what it was designed to do. Of course, we don't just secondary line the tunnels, we also secondary line the shafts. This is a picture taken just before Christmas from pit bottom up at Acton at the top of the tunnel, or at the head of the system, I should say, and that's looking up at the bottom of the slip form. That's been proceeding up there through November and December and is now more or less complete. Moving on to a different type of site, Putney. This is a highly aesthetic, highly architecturally challenging site. This is what we're trying to do. We're intercepting flows underneath the bridge and conveying it to a new foreshore structure, similar to the others. This is what it will look like in the future. And well, actually, the future is more or less now, to be honest, because We are, this is an old photograph here. This is probably autumn of last year. The site is nearing completion now that the lids are all on, the access covers are on, and we're now very much in architecture and landscape delivery on that particular site. But I've included these photographs here just to show you the sort of high quality finish that we're achieving out there with granite on the front face of this new foreshore structure. And that's some of the text we're seeing for putting the embankment there, just saying tunnel 32 meters below. The photograph at the top left, I think I took this photograph a couple of weeks ago. That's between the river wall temporary sheet cofferdam piles and the new river wall on the right hand side. And I'll march through a couple of these fairly quick here. That's an example of a mechanical kiosk on one of our sites. So it's a simple blockwork structure that will house some hydraulic power units, but that will be clad in granite, and then there'll be some artwork hung off that structure. So Blackfriars, those of you familiar with Blackfriars Bridge will recognize this photograph. This is circa 2014. Big job here, very large site, 2 major CSOs to intercept in the foreshore, new foreshore structure. Before we could do anything, we needed to shift this existing Thames Clipper jetty. So that was carried out. I'll just go to this picture here. That's what we did. We shifted the Clipper pier to the other side of the bridge, and that allowed us to concentrate on the main site itself. Now, this site is very challenging in that the shaft is to be constructed on the left-hand end of this cofferdam, and one of the main interceptions is right underneath Blackfriars Bridge at the far right. And I showed you earlier in some of the sections that we have, strategic utilities running along the embankment, as well as the low-level sewer, as well as proximity to bridges and existing live river walls. So in order to overcome supreme challenges with settlement, and there is a need to construct a connection culvert from the shaft all the way over to that bridge, the team came out with a sort of phenomenal proposal here, which they executed in August 20. So the need was for a 100-meter long connection culvert that's 9 meters high. It was constructed within that cofferdam, just in the middle of that photograph as you look at it, within a dry working area. And then ultimately that cofferdam was flooded. And that culvert, which is a 3,700 ton section of concrete culvert, was floated out on a high tide and maneuvered into place to give us the connection into the CSO. That's what it looked like in sort of 4D modeling times. That's the culvert being constructed, cofferdam flooded, and then the culvert being floated into place. And then the team get on with the next phase of the job. This is what it looked like, 2020, August bank holiday weekend, high tide, being floated out into position out of the cofferdam. And then some more photographs of her on her way. And then this is a very recent photograph of some operatives walking through that culvert now. It's in place, it's in position, and it's a fantastic piece of work. And that piece of temporary works deserves a presentation in its own right. But it did win the British Construction Industry Awards in 2021, the Temporary Works Initiative of the Year. Hell of a piece of work done by our colleagues at CVP there. And at Blackfriars, that site, this is ultimately what we're aiming to achieve, and we're not too far off it now. This is a photograph of probably circa 2023, late 23. And finally, Hammersmith, just delve into this. This is a slightly different take in events. So Hammersmith, another extremely complex site. This is upstream of a pumping station, turning 43 cumex into a shaft. I'll rattle through these photographs here. They're fairly standard of our major construction. And what I wanted to get to was some photographs here of the shaft showing that vortex tube in position and in its concrete surround at the bottom and the concrete surround at the top. And the photograph in the middle is one of our spring-loaded access covers, mechanically assisted access covers. But one of the fundamental challenges we have at Hammersmith is that we need to operate within a live environment, a very large live environment. So this is the inlet channel upstream of the pumping station. It's approximately 18 meters deep. It's about 8 meters wide and about 15 meters long. And inside that chamber, we need to construct a wall which is circa 7 to 10 meters high with twin penstocks in it, which will allow us to deny flow going into the pumping station and turn that flow through 4 new openings in the inlet channel wall into Tideway. So a lot of concreting works needs to be done in a live sewer environment. This is what it looks like. typically after a storm. So what we have here, we've constructed bulkheads either end of the works area. Those bulkheads can only be built so high. There comes a point when the height of those bulkheads would preclude sufficient flow coming over them at high weather events, and we could cause flooding issues in the system. So what we have is a series of flumes that convey most of the flow through the work area. But there does come a point, and quite regularly these days, there does come a point when this area does flood. And we have a substantial team down there trained to get in there and clean it out. This is what it looks like after a storm event. It's not pretty. I hope I haven't affected your tea. But this is what our men and women are dealing with on a daily basis to sort of achieve these interception works. This is what sewage in London looks like in the sort of volumes we're talking about. And they go through an exercise of cleaning it out to produce this sort of finish to allow us clean concrete to carry on pouring and creating penstock walls and doing what we need to do. And it's a phenomenal piece of work down there. Massively proud of what the team do there. Some pictures at Hammersmith up high level. These are just some upstands going in, nothing too particular. And down in one of our tunnels, this is a flow restrictor wall, so just some dense rebar being fixed to construct the wall, another version of a baffle wall in the tunnel. So I was asked to talk a little bit about COVID and what it meant for Tideway. So in March 2020, most of the work stopped, and we ultimately restarted in May of 20. Now, at the time of the stoppage, we were about 60% through tunneling on the job. We had 3 TBMs underway, and at that point in time, we had 26 live sites. For me in West, it was probably the worst time in the 8 years I'd been on the job at that point for us to have a stoppage on the job. We had our main tunnel TBM was within the zone of influence of Hammersmith Bridge, which those of you familiar with Hammersmith Bridge will know that it's closed due to structural concerns in West London. So that was a very sensitive bridge which we were approaching. And our Frogmore TBM, that smaller TBM, was underneath some river walls, which were a big focus for us. They were quite sensitive in Wandsworth. So we went through a very intensive focus on safe shutdown and what it was we could safely shut down and where could we do it. And I think what was unique, certainly unique for me, and I think unique for the team, was that we were faced with a situation where we didn't know when we get to restart. We didn't know, was this for days, weeks, months? And there does come a point in time when a TBM mightn't restart at all. You mightn't, that ground could consolidate and come on, and that could be game over for you. So massive concern about, it's one thing to safely shut these things down, but can we restart them, and where are we relative to that restart? And what's the worst case scenario for having to restart in that area? So we did get our main tunnel TBM past Hammersmith Bridge before we stopped. We got her underneath St. Paul's playing fields, and we got the Frogmore TBM out under the river. And at that point in time, we stopped everything except the Putney Connection Tunnel pipe jack, which was deemed not safe to stop. It was safer to keep going, which the team did. So that was our only site which carried on right through COVID, with intensive activity to monitor whether we were going to lose operatives or materials, through that crazy March, April, May period. The team got the job done. I was part of the tech advisory group on the shutdown and startup. It's probably one of the most intense periods of my career to date, those couple of months. But a hell of a learning experience. And since then, probably like all of you on projects, we've had materials challenges, lead-in times, availability materials continues to be an issue and a challenge. That's public knowledge now. I think from the Tideway report was recently issued just prior to Christmas, and the project position now is that COVID has added 5 months onto our program and probably 190 million of cost so far. For me, the personal lesson, Murphy's Law, my namesake, we're used to planning for all eventualities, but I don't think we ever really planned for an unknown stoppage for an unknown amount of time. And the idea of having to understand whether you're going to run out of men or materials never really crossed our minds, I don't think, that a pandemic could arise and could cause the impact it did. I personally now scrutinize supply chain risk a lot more than I probably did previously, just trying to understand, where designers getting their sourcing their waterproofing materials or bearings, or where are these things coming from? Because I recall at the height of COVID, I was faced with situations where we were, needing something from southern Germany, and the plan B was northern Italy, and then the plan C was northern Spain, all of which were COVID hot hotspots at the time. So plan for all eventualities and scrutinise supply chain risk. A number of innovations on Tideway, and I'm just coming to the end of this presentation now. The one I wanted to point out here was shutter strip, which is one I was proud to accept and help the team get over the line 2 years ago. It's one, we had a serious sort of occupational health risk in that we've a lot of scabbling to be done on concrete to prepare the surface for concrete to be poured in it, and the team came up with a chemical tape which effectively is fixed onto the inside of the shutter, so that once the shutter is struck, that tape can be pulled off and you're left with the surface finish on the bottom photograph. So it's effectively a ready scabbled, latent free bit of concrete ready to go, and that really reduced the amount of time we had operatives scabbling concrete with wire brushes and all the rest of it with high pressure water. Virtual reality cubes have been a success in the job, as well as the secondary lining shutter automation. Sesame water testing alternative. Those of you involved in hydraulics and testing tanks and sewers will be familiar with the need to air test, or not air test, to water test through a drop. You fill up that tank and you wait for it to drop over a period of time. I mentioned earlier we've got 1.2 million cubic meters of storage in these tunnels and chambers. We couldn't afford to need water to fill up all of these chambers and structures to test them. So we've effectively come up with a scheme which utilizes Foucault tubes in the joints and pressurizing those Foucault tubes with water post injections to see can they hold the pressure. But that's more for another day, I think. So look ahead, just coming to the end of this now. We're in 22 now. This is what we're on track to deliver. We're very much considering now commissioning. We're heavily involved in pre-planning for commissioning on all sections, and we're full steam ahead for handover in 2025. Good progress as of 4 o'clock today. This is where we are. We're 72% in line with our target. In tunneling, so 25.5 kilometers of tunneling progress. 11.3 of secondary lining completed. On east, Selina has progressed 2.5 kilometers in the last period, and she's well on her way to Abbey Mills. And we now have full connection all the way from Acton right through to the back end of Selina out east. So we're well on our way to completing these tunnels. I've mentioned the Tideway interim annual report, so we're still on track for 4.2 billion overall cost, and our project completion date, as I said, is 2025. And late last year, I'm happy to report that Tideway was recognised at the NC Tunnelling Awards with 5 award wins from people and contractors working on the project. So it was a phenomenal year for us last year. Some architectural impressions of what Putney will look like. This is Bazalgette Embankment, which is that Blackfriars site we've touched off through the presentation. And then that's the end. So I think for us, what I'd just like to say that this is a project it's not just about building a tunnel, it is about building a lasting legacy for London, its residents, its visitors, and the wider construction industry. Thank you, and I'll take questions. Phil, if you like.
Thank you very much, Colin. So I have a number of questions coming through via Zoom. So if you do want to, for those watching, if you want to add your questions in there, I can read them out to Colin. But is there anybody in the room any questions first?
Yeah, I'd like to ask, was there anything as part of the design that you decided to change halfway through or partway through the project where you thought, okay, this isn't working, we need to rethink? Or did you have a design from the outset that worked?
I think the reference design was fairly fixed in terms of the hydraulic geometry, what we needed to build. There was a lot of challenge on the secondary lining, the thickness of the secondary lining, because of the complexity of the secondary lining. Do we need it? If we do need it, how thick does it really need to be? I think the use of fibre reinforced concrete has really come on the job. I think that's been heavily utilised to try to cut down on rebar. I think I think it's really in the constructability, the likes of that road in Barn Elms, where that might have previously been a sort of a tarmacadam standard road, to move to recycled plastic, to move to recycled materials. I think that those sorts of things have been key drivers through the job. And understanding the testing and handover criteria for the job, things like that SESB alternative tests, is it really right to fill up, to ask Thames Water to give us 1.2 million litres of 1.2 million cubic meters of water to do a test on this? There must be a better way of doing it. So innovation like that, I think, is what's come on through the job.
Thank you very much. So the first question I have from the function on the Zoom is, I know you had a slide on innovation already, but were there any innovative or bespoke engineering solutions required for any aspects of the project? So any solutions that might not used on other similar large-scale civil projects? Is there anything you want to maybe focus on?
I think if I just go back to the list, a couple of things I would like to focus on. I'd like to focus on safety just briefly. The EPIC safety induction is something that, to the best of my knowledge, was unique in the construction industry. It may well still be unique. I think it is starting to come in. Effectively, it was actor-led safety training. So he was putting operatives, engineers, everyone on the job into live incidents effectively, and asking you to partake, taking you through an incident, taking you through a police interview, you know, at the wrong end of things, taking you into a person's house when a bereavement or an incident has occurred. It was really, really hard hitting. It's probably one of the most powerful safety training pieces I've ever undertaken. It was so powerful that one day in the canteen I was having my lunch, and there was a black hat foreman, you know, really laying into a young guy, and I was thinking that this needs to stop. I didn't quite appreciate that this was actually part of the training. It was made to get people to look up and say, hold on a second, what is happening over here? Why is he screaming at him? What's that all about? Really, really got you thinking. So I think that's one thing. I think the secondary lining shutters on the job are fairly cutting edge. I think what we're doing with secondary lining concrete in general is very cutting edge. It's pretty much out there. Secondary lining has been done in many places, but I think on the way we're doing it here is pretty unique. That shutter strip there is the first time it's been used anywhere. It's a brand new way of looking at scabbling, I think. So things like that probably spring to mind. I think temporary works innovation. We're looking at, we've got huge benching in our shafts. So at Carmouth Road, the benching is nearly 16 meters high at 1-in-1 slope. You know, it's sort of 2,500 cubic meters of infill material. We're going to take all our legato blocks used on the hoarding around the sites and use them to infill our benching. So we'll reuse a lot of material there. So things like that.
Thank you. You mentioned secondary lining there a number of times. I've got a question here. What is the purpose of that secondary lining?
The purpose is to protect the primary lining. So the primary lining invariably provides the water tightness for the tunnel, and the secondary lining is effectively an abrasive protection. So coming back to the design life of 120 years, you need to be sure that we're not going to, you know, if we relied on primary only, we'd be relying on the segment, we'd be relying on the gaskets between the segment. And given that we run this tunnel through a series of aquifers in London where water is abstracted, there's a risk balance to be had in what is reasonable to expect in terms of durability from a segmental lining. So the secondary lining gives that added assurance. It also helps flow characteristics in the tunnel. It gives a smoother finish and moves things faster.
So secondary lining seems to be a very popular topic here. Okay. So the next question on it is, what level of roughness and permeability were you looking to achieve with the secondary lining?
I think I'd have to come back to you on that one, Phil.
That's too technical. Thank you very much.
Deep.
Okay then, so how did the variable dig conditions affect overall procurement and management of the project, particularly with respect to the variety and availability of subcontractors?
It affected it fundamentally from day one. So I mentioned that we've talked about West, Central and East contracts. West, Central and East contracts were set up because of the geology of London. So the West contractor would be predominantly tunneling in clay. That would mean that the sort of TPM he'd need and the shaft construction techniques he'd need would suit that environment, whereas the Central contractor is dealing in the Thanet sands and gravels. So his set of skills are really orientated towards there. So the contracts were laid out on the basis of London geology.
Thank you very much.
Okay.
So I've got one question left on Zoom. So if you do have any more, please get them in quickly. Maybe those in the room, maybe be ready to ask some as well. And it's an interesting one to finish up on here. So I've got a question that says, what causes the apparent brown color of the river, and will this change on completion?
No, is the answer to that. So the colour of the Thames is as a result of the sediment that is stirred up from the base of the Thames. It's not the sewage that turns the river that colour. So the river will remain that colour in perpetuity, I'm afraid. It will never look blue. It won't look like the Aegean Islands or anything like that. But
Thank you very much. Yeah, I wasn't too sure what the answer would be there for that one.
what I can tell you, and I hope you're not eating your tea, but the sewage sits in a blanket. So about 1 metre below the surface, there's a blanket of sewage, which is anywhere from 0.5 metre to 1 metre deep. And that blanket moves up and down the Thames as the tide comes in and the tide goes out. And it takes about 2 weeks. And we did do this, we did do actual yellow duck dropped off a bridge versus sort of modelling at the time. How long does it take a rubber duck from Hammersmith Bridge to get out into the North Sea? And it takes about 2.5 weeks. And yeah, that's what the modelling said, that's what the rubber duck said, and that's why we have the problem we do in London.
Thank you. So we do have another couple of questions coming through. So the next one is the EU Urban Wastewater Treatment Directive. Is that still applicable post-Brexit?
Oh, no, we're delving into tricky waters. I think it is applicable. I suppose you can look at it from two perspectives. What do we want to achieve as civil engineers in society in terms of clean water? What's the right thing to do? Is it right to tear that up and forget about it? Probably not. Maybe there's a halfway house between those standards. I think as we stand right now, as I understand it, that framework still stands, but it's adopted by the UK until the UK comes up with replacement guidance. By the time that happens, hopefully Tideway will be complete, and we wouldn't need to worry about that question, I think. But I think it's a wider question than just we're out of Europe and should we down tools and relax the rules. I think we need to seriously think about what's right.
Thank you. And this next question is one I was going to ask as well. Is what happened to all the earth that was removed?
It's a good question. Out in the Thames estuary, on the south side of the estuary, as part of an RSPB bird sanctuary, effectively, the clean muck has been sent down there, much the same as a lot of the muck from Crossrail did, and other large jobs in London will probably continue to do for the next couple of years. It's all about constructing wetlands and bird sanctuary in the estuary.
Okay. So still another 2 questions here to go. So are there any concerns over, says H2S, from the raw sewage corroding concrete?
Yeah.
Or does the liner cater for this?
There is concern. It's a large concern, and that is a reason why we do have a secondary liner. When we design concrete as part of the cover to rebar, or the cover that we need, there is an additional level of cover included to account for H2S. So we're acutely aware of H2S and issues around septicity within the tunnel and keeping things moving, and it's the H2S issue which led to the likes of the air treatment bit that I talked about, the active ventilation, the passive ventilation, refreshing the air, continuously changing it. But H2S in concrete is a big deal.
Okay, so, thanks for that. And final question I have here is, can you describe more about the alternative to CESW2 water test?
It says we water test. So if you think of a traditional water drop test, what you're trying to understand is, as I've poured my concrete and I've created construction joints, are those construction joints sound and watertight? Now, not watertight to 0, but watertight to a leakage rate defined in CESW. And you watch the water drop and you back calculate and you make a decision on the efficacy of your joints. We're coming at it from the other end, in that we've got Foucault tubes within the joints. Those Foucault tubes allow joints to be injected. So we can inject a joint with a cementitious material to ensure that the joint is sound and watertight. We then, once that's cured and set and gone off, we then inject that tube with water, and we've a stop end at the other end of the tube. We hold the pressure in that tube. So that tube, in theory, could allow water out, But if the joint is sealed around the tube, the water isn't going to leave the tube. So if the tube holds pressure for a period of time, then that tells you or indicates to you that you likely do have a watertight joint. You'll see it, but you'll also see it on the pressure gauge. So it does put a reliance on a Foucault tube, and it puts a reliance on workmanship and installation of Foucault tubes and joints. But it does give us an easier way and more sustainable way of testing those joints. And it's proven quite successful. You know, we've been doing it now, I think, for about a year, testing joints this way, and the numbers are stacking up. I think it is fruitful.
Very good, thank you very much. I think there's one more question coming through, and I think it's following on from that is, what is the remedial works if a joint fails?
Injection, effectively. You know, you're coring through the joint, you're injecting in behind the joint. If you've got a tube in the joint, if you're fortunate to have a Foucault tube, you'll inject through the Foucault tube and try and inject along the length of the tube. But if you don't have that, we'll probably core through and inject in behind it and chase that leak right around the joint until we've stopped it. Basically, it's as simple as that.
Okay, thank you very much again for that. That's the last questions from Zoom. I think we've another couple of questions from the room here. If you could maybe raise your voice so those in the webinar can hear.
It's really when it's about inspection and maintenance. Have you got a protocol for actually inspecting the sewer in the long term? Because it's got 120-year design life.
Yeah.
How do you access the sewer? And do you have to actually close down sections of it?
Yeah.
For inspection.
Yep, it's a good question. We have a 10-year maintenance frequency that we design for, that we plan for. So we expect the tunnel will be closed every 10 years. And in that maintenance event, the whole tunnel is shut down. And the period for which it's shut down is TBC. You know, it's yet to get to that development stage. That's when you'll have contractors on board to design, you know, that maintenance event. But the idea is that, and the reason we had so many access covers on that slide I showed earlier, is that we've no ladder access into the base of the shaft by choice, by design. We didn't want that. The access to the base of the shaft is via man rider. So you're lifting off covers. Those covers are either 3x3 or they're 7x4 in size. The 7x4 covers are on our main drive sites, the big shafts, and they're sized on the basis of a vehicle akin to a Land Rover being dropped into the base of the shaft, and that Land Rover would drive along the shaft, drive out of the shaft through the tunnel and inspect the tunnel lining as they go. That was the sizing of it. I think we've moved on since, you know, that thinking was probably 6, 7, 8 years ago. But that's the theme. A vehicle will go through the tunnel, inspect the tunnel lining. Probably at this point, technology has come on that will probably be an autonomous exercise, and then the material will be reviewed by engineers and assess whether we actually need to get people in there. We've seen experience on the Lee tunnel, which is very, very similar to our tunnel and is in operation now a couple of years. And when that was shut down, it was crystal clear. You know, it was a really, really good condition. So the expectation is we have the ability to get humans down there in vehicles to do inspections and do repairs if necessary, but it's a full-scale shutdown. And so that's 10 years, that's a big shutdown. Normally, in terms of penstocks and flap valves and all the mechanical kit, we'll have a man in a van type arrangement coming up to sites to inspect penstocks, inspect the MIC elements. In terms of civils, we've gone through a fairly heavy, intensive exercise of making sure that we've got the capability to get CCTV access to most of the concrete surfaces in these shafts and in these inaccessible areas, so we can inspect them remotely and see what the condition is before sending in someone. Because one of the big challenges for us is that, you know, in order to lift a lid, in order to lift a 7x4 lid, you need a 40-ton city crane is going to come in and sit on top of that shaft. So before you put a crane on that shaft, you need to inspect the beams holding up the roof slab to make sure it's sound. So there's a period of investigation, probably about 2 years before that 10-year event, you know, CCTV and that from a structural perspective to investigate those beams and covers. Does that answer?
I've got kind of a follow-up question. Do you have to clean the tunnel before you inspect it?
The aim is no. You know, it's been designed to be self-cleansing. You know, as I said, we've got big benching in those big shafts. We've got benching, you know, just like you see in a normal manhole, but multiplied by probably factor of 20 or 30 times in size. But the idea is that it's self-cleansing. As I said, the experience from Lee Tunnel suggests that that was crystal clear. And we've got a fairly similar hydraulic arrangement to them. So hopefully no, but we've planned for it. We planned for the ability to get waste skips up out of the base of the shaft if stuff needed to be dug out.
You pray it doesn't rain while you do it.
Well, you'd revert to today's scenario. So when Tideway is shut, flows will discharge the river in the fashion that they would today. So the period under which you'd be shut would obviously be a fairly tightly controlled period, because when you're not open for business, you're back to 50 or 60 discharges a year, and you know those figures I gave at the head of the presentation. Okay.
Thank you. Conscious of time, I think we have one more question from the room.
That was pretty much the maintenance thing as well, so I stole my thunder. But no, I suppose just what percentage of time would you expect it? Is the tunnel's only used as an overflow, essentially? So what do you expect it to be every couple of days?
Yeah, about once every 6 days. There'll be some level of flow going into it. So if you think we're taking discharges down from 40, 50, 60 times a year, depending on which CSO, and we're taking them down to 4, that broadly equates to about once every week and a half or so. But when you play it out, you know, they kind of bunch up. You get more intense discharges through the summer. You actually get some less discharge in the winter. The bigger flows are in the summer when you get the intense rainfall in London.
Now, obviously, you mentioned you're designed for 1 in 15 years. Are you fine with the change in weather patterns of 1 in 15 years when you redefine? You know, is that something that you're conscious of, or is that?
Yeah. So our 1 in 15 is a factored 1 in 15 to the standard 1 in 15 year design storm for you know the UK standard drainage would require. So we factored it to account for sort of an extrapolation of intensities over a period of time. So looking when I mentioned about catchment modeling, so the team have looked at the rainfall intensity over a period of time and sort of projected, well, today's 1 in 15 will look like this quantity, tomorrow's 1 in 15 will look like that. But what you're really, as I sort of touched on briefly, we're less concerned about what a 1 in 15 year looks like. We're more concerned about what the sewers can actually deliver to us. There's a finite quantity that the sewers can actually get to the tunnel. And when you sort of back calculate what that is, it's sort of a 1 in 15 year storm.
So you think ultimately we'll have to add additional subs to the system as well?
Ultimately, yes. You know, and you probably know as well as I do that that's now part of the sort of standard design guidance. You need to put suds upstream and try to store rainfall online, inline, you know, up at the source. But that's the way it needs to go. But yeah.
Okay, thank you very much, everybody. There are lots of praise coming through in the chat function. Colin, great presentation, very informative. So thanks again from the GB region. Really excellent presentation. And we look forward to the next episode of it.
Lovely. Thanks very much.
Thank you.